Greetings, nerds. Let's actually talk about the derivative of sine. So the derivative of sine, if we go back to the limit definition of sine, we arrive at this difference quotient, right? The limit as h goes to 0, sine of x plus h minus sine of x all over h. Again, that's the definition of the derivative. But something, going back to pre-calculus, you want to remember is that, well, sine of x plus h, we can actually use a sum identity in this case, right? So sine of x plus h is sine of x times cosine of h plus sine of h times cosine of x. Now again, if that's something you didn't fully remember, or man, it's been a while, that's okay. Just remember those two things are equivalent. I give it to you. What that means though for us is we can take the right side of that equation and transform that first term in that difference quotient to this. What we're going to do now is a few different things. First thing is the last two terms here, I'm actually going to flip those around. It's just going to make my life a little easier. And then I want you to notice that the first two terms now in that numerator both have a sine of x in it. So what I'm going to do is factor that sine of x out of both terms. The now second term, the sine of h times cosine of x, those two are being multiplied. Multiplication is commutative, so it doesn't matter the order in which I multiply them. So what I'm going to do is actually flip that order. Again, I promise you it's going to make our life a little bit better. I now want you to just focus on the fact that we have two terms in this numerator divided by h. So that being said, what we can do is think about that term is being divided by h, and then plus our second term being divided by h. So h is the shared denominator, which means that I can rewrite that, that quotient in terms of two separate fractions. It's sort of like I'm splitting them up, if you will. So then looking at this, what we can now do is we have a limit of a sum, which applying that limit property simply means that we can apply it across that limit. Now I really want you to notice something here that's really special. We have h going to 0, right? So this limit is affecting h. That's the way that you can think about it. In the meantime, though, what we have are these two terms, there are these two components, the sine of x on the first and cosine of x on the second. They're both being multiplied. So what we have are things that are not changing with respect to h. So that being said, sine of x in that first term doesn't change as h tends to 0, which means that the sine of x is behaving as a constant over that limit. The same thing is true also about the right-hand limit. You notice that cosine of x itself is also a constant. Again, constants being multiplied to a function inside of a limit means that we could bring those constants out front. And so because the sine of x and the cosine of x are both constant over this limit, then what we can do is bring those out front and rewrite our derivative of sine this way. So now we're looking at the derivative of sine, and we've changed it into this weird looking sum. We have sine of x here times the limit of cosine of h minus 1 all over h. We have plus cosine of x, and we have this other limit. Well, as it stands, what we can probably now do, and you can probably imagine, let's tackle what are these limits equal to? We have two limits, and if we can figure out what those are conveniently, that would be great. Because if you notice, those should be a specific number. So all that being said, I want to hyperfocus on the first one. It doesn't matter the order here, so let's bring that out of context for just a second. So looking at this first limit, here's what I'm going to do. I'm going to look at the inside of that cosine. And so inside of this cosine, I'm going to add a 0. And so if I did it just perfectly, it would look like this. Again, nothing's changed. And now what I want to do is hyperfocus on that 1, that special 1. As it turns out, going back to, again, trigonometry, right? We understand that 1 is also cosine of 0. So cosine of 0 is 1. What I'm going to do is replace the 1 then with that cosine of 0, and we have this. Now for this next part, it would require that you know a little bit of calculus, but suffice it to say, here's what we're looking at, right? We have this whole cosine thing. Well, these cosines, if you really thought about it, are just function names in and of themselves. It's sort of like saying f, if you will. And of course, these zeros are really like a. So it's sort of like, like a constant. And so what we can do is just think of them as a and put them into We can also look at the zeros and just, right, those are just some number, call it a, for instance, as you probably can imagine. And what we have now is this, which again, if you've had a little bit of calculus, hopefully you've seen this before this point, that numerator being f of a plus h minus f of a should be a very familiar person. In fact, we can just sort of imagine in our minds that that limit you're looking at is the limit as h goes to 0 of f of a plus h minus f of a all over h. That is the definition of a derivative. So going all the way back, this original limit right here that we're trying to figure out is, truth be told, a derivative in and of itself. It's the derivative of cosine evaluated at 0, which graphically we can imagine that to be the slope of cosine at 0. So let's go look at the graph of cosine. So here's our graph of cosine, and if we just hyperfocus on what's happening at x equals 0, well, there is your slope up top on that maximum. But the more you think about it, I'm sure you can see that's clearly 0, right? That's a slope of 0. So if that's a slope of 0, well, guys, that means that entire limit, right, equals 0. That's what that limit we learned is equivalent to, which means we can replace our limit in our original derivative expression with 0. So 0 times anything is just 0. It completely cancels out. So, guys, the derivative of sine just now boils down beautifully to this. So what we have now is one last final limit that we need to inspect. Just as before, let's bring it out of context. Just as before, I'm gonna add some zeros, but this time I'm not just gonna add a 0 inside. I'm actually gonna subtract a 0 outside my function. So clearly, again, I haven't changed anything. It's that latter 0 there, that minus 0. That's the one I really want to notice. So let's bring that out of context for a minute, right? Remember from trigonometry that sine of 0 is 0. So let's replace that 0 with sine of 0, and there it is. And so now, again, just as before, what you're looking at is, in and of itself, a derivative evaluated again at 0. In fact, what we're looking at is the slope of sine at 0, the derivative of sine at x equals 0. As before, let's take a look at a graph. So here's a graph of sine. If we were to put a tangent line on that graph, and again, remember, what this entire limit is equal to is the slope of this tangent line at x equals 0, which, if you'll notice, has a rise of pi halves and a run of pi halves. Guys, that's a slope of 1. So if that's a slope of 1, then that entire limit equals 1, which beautifully means that we can replace 1 in that equation, and there we have it. The derivative of sine is actually just cosine. Take care, nerds.